This is Physical Chemistry, Part 3, Quantum Chemistry, Chapter 20, The Hydrogen Atom, Section 20.1, Formulating the Schrodinger Equation. In a hydrogen atom, there's only one electron. The energy of this electron is the sum of its kinetic energy and the attraction it feels from the proton. The interaction between two charges, Q1 and Q2, is given by this equation. This V is the potential energy, Q1 times Q2 over 4 pi epsilon R. 1 over 4 pi epsilon is the so-called Coulomb constant. R is the distance between the two charges. When Q1 and Q2 have the same sign, we have a positive V. That's repulsion. When Q1 and Q2 have opposite signs, we have a negative V. It's attraction. What about this epsilon 0? Well, it's commonly called the vacuum permittivity. It's a physical constant. The value of epsilon is here. 1 over 4 pi epsilon is roughly 10 to the power of 10. Well, because 4 pi is roughly 10, and this is roughly 10 to the power of negative 11, so 1 over 10 times 10 to the power of negative 11 is roughly 10 to the power of 10. So what's the unit of 1 over 4 pi epsilon? I think you can just do some unit analysis. The unit of 1 over 4 pi epsilon is the unit of this potential energy times the unit of distance divided by the unit of this charge squared. So the unit of 1 over 4 pi epsilon should be joule times meter divided by Coulomb squared. Now we can write out the attraction of the electron in the hydrogen atom. It's negative E squared over 4 pi epsilon R. R is the distance between the electron and the nucleus. The reason we have a negative sign here is because the proton and the electron have opposite signs. What about the kinetic energy of the electron? Well, this electron can move in all 3 dimensions. Therefore, the kinetic energy operator of the electron is this: negative h bar squared over 2 m sub e times the sum of these 3 second derivatives. M sub e is the mass of the electron. It's roughly 9.11 times 10 to the power of negative 31 kilogram. H bar is the reduced Planck constant. We can also convert x, y, z to r, theta, and phi in spherical polar coordinates. How do we do that? Let's look at this. So we have x, y, and z to define the position of the electron. And this is the position of the nucleus or the proton in the hydrogen atom. We can also define the position of the electron with r, theta, and phi. R is the distance between the electron and the nucleus. And this r with an arrow is a vector. It has a direction. So between this vector and the z-axis, there is an angle, theta. And then if we project this r vector onto the xy plane, we have this vector. And this vector can be defined by the length of the vector and its angle with the x-axis. So the angle between the projection of r on the xy plane. So this vector, this is actually a vector. Between this vector and the x-axis, we have another angle. This is phi. Alright, so if we know the values of r, theta, and phi, we can also define the position of the electron. Theta corresponds to the latitude of Earth. Phi corresponds to the longitude of the Earth. What's the difference? In quantum mechanics, by convention, we say this theta is from 0 to pi with a range of 180 degrees. Well, if you look at geography, it's defined between North Pole, 90 degrees to 0, the equator, and then between the equator, 0 to South Pole, 90 degrees. So it's more like from positive 90 degrees to negative 90 degrees. In quantum mechanics, we often use 0 to 180 degrees. Now this is longitude of Earth. Usually it's between west 180 degrees to 0 and then to east 180 degrees. But in quantum mechanics, we simply just say, well, this phi is between 0 and 2 pi, or 360 degrees. Now let's get back to the conversion. So we want to look at the conversion here. Z is r times cosine theta. So this Z is r times cosine theta. So this angle is theta. So that's pretty easy to see. And then to define x and y, we need to understand that if we project the r vector onto the xy plane, well, the length of that vector on the xy plane is r times sine theta. It's not r anymore, it's r times sine theta. And then to define x and y, we need to multiply this r sine theta by cosine phi for x, by sine phi for y. Alright, so this is basic trigonometric functions. And r can be expressed as a function of x, y, and z. This is how we define phi. Tangent phi is y over x. Tangent theta is, again, the projection of r on the xy plane divided by z. This is how theta is defined. Well, of course, you can use sine and cosine functions of phi and theta as well. Right? So this are just some of the definitions. So again, I want you to look at this picture and understand that theta corresponds to the latitude of Earth, phi corresponds to the longitude of Earth, and therefore theta has a range of 180 degrees, phi has a range of 360 degrees. And this theta value can be 0, from 0 to pi. It can be 0, it can be pi. It's different. Cosine 0 is 1. Cosine pi is negative 1. Alright, so different. There's a difference. But over here you can see phi can be 0, but phi cannot be 2 pi, because when phi is 2 pi, well, that's simply 0. How do we convert the kinetic energy operator to polar coordinates? Well, we'll just use the chain rule in calculus. This is the first derivative of the wave function psi with respect to z. And because r depends on z and psi depends on r, theta depends on z and psi depends on theta, and phi depends on z and psi depends on phi, and then we have this chain rule over here playing its role. And similarly, we can expand delta psi over delta x and delta psi over delta y. As long as you realize that there are 3 intermediate variables, r, theta, and phi, between psi and x or y or z. Alright, so this is the chain rule. Again, this is psi, how psi depends on r, and then r depends on z. Alright. Well, let's skip the derivation. after converting the kinetic energy operator of the electron into the spherical polar coordinates, we get this equation in r, theta, and phi. All right, so this part is the kinetic energy operator. This part is the potential energy operator. So we are applying the kinetic energy operator to psi, and then potential energy operator to psi. We sum it up. We get the total energy operator being applied to psi. What's the total energy operator? It's the Hamiltonian H. So you are looking at H psi equals E psi again. Oh, by the way, the supporting information contains around 20 pages just to convert the kinetic energy operator to the spherical polar coordinates. In quantum chemistry, we simply solve this Schrodinger equation for the hydrogen atom, and then we solve similar equations for many other atoms and or molecules of interest. And once we solve this equation, we will be able to get the so-called Eigen functions of the Hamiltonian operator. Those are the wave functions of the system of interest. And we will also be able to get the total energy of the system and all other physical observables for that system. What about the kinetic energy of the proton or the nucleus of the hydrogen atom? I want to say the kinetic energy of the nucleus of the hydrogen atom is negligible compared to the kinetic energy of the electron. So you can prove this here. Assuming we're just looking at one hydrogen atom, and for simplicity, let's say this hydrogen atom is not moving. All right, even if it's moving, if we focus on its internal energy, the translational energy of this hydrogen atom is not of concern. So let's say this hydrogen atom is not moving. All right, but well, you can argue this hydrogen atom on Earth is rotating about the sun, but really I don't care about that. Let's say the hydrogen atom is not moving, and then we have this conservation of momentum. So mv of electron is negative mv of the proton, or the nucleus of the hydrogen atom. And then we can square both sides. We get this equation. So we have equation here. And because the mass of the proton is 1800 times that of the electron, so we have this inequality here. All right. So this top is equal to this top. All right. But the mass of electron is much smaller than the mass of proton. All right. So that's why we have this inequality. And if that's the case, we can tell immediately the kinetic energy is much greater than the kinetic energy of the proton by a factor of 1800. So that's a lot. Although that's the case, we can still include the kinetic energy of the proton, or in general, if we're looking at other atoms or molecules, we can include the kinetic energy of all the nuclei, but we'll have to study statistical thermodynamics to understand how to include the kinetic energy of the nuclei in the internal energy of the atoms and the molecules. All right, so a lot more math coming.